Okay, this is exam 1 for physics 102. The magnitude of the charge on an electron is approximately electron is 1 - 1.6 times 10 to the minus 19. So that answer is going to be B, just 10 to the minus 19. When you charge an object by induction, you do which of these? Do you touch the ball with the charged object? No, on that one, because you don't touch an object when you charge it by induction. Do you move electrons from your finger to the ball? No, you don't. No transfer of charge from one object to another. Do you induct the ball with charge? I don't even know what that means, to induct a ball with charge. But you do bring a charged object near, but do not touch the ball. An electrical insulator is a material. Which of these? Must be a crystal? No, not necessarily. Has more electrons than protons on its surface? No. Cannot be a pure chemical element? No, no, no. Through which electrons do not flow easily. That's the right answer. This diagram shows two pairs of heavily charged plastic cubes. Cubes 1 and 2 attract, cubes 1 and 3 repel. Which of these illustrates the force on cube 2, on cube 3, and cube 3 on cube 2? So let's just imagine that this is a negative. That means that this has to be positive. And if this is negative, this also has to be negative. So we're looking at cubes 2 and 3. They're positive and negative, so that means they're oppositely charged, so they are going to attract to one another. So the answer for number 4 is C. Which of the following diagrams potential on the x-axis equal to 0? All right, so imagine you take a point, say right here, and I ask myself, do these potentials cancel? And they do not. Notice actually they're both negative, so they don't cancel, both negative here. So I have a negative potential all along that axis. Here, let's imagine, do those potentials cancel? Now I have a positive and a negative charge, but they don't cancel because they're not the same distance from that point. So no on that one, no on that one. And here, similarly, I have positive and negative charges, but they're different distances from the axis. So the answer is D, none of these. Number 6, two uncharged metal spheres, L and M, are brought in contact. You bring a negatively charged rod, is brought close to L. Let's see, sorry, this should have negative charges. Let's see, I'll fix this. I'll fix that on the test. Is brought close to L but not touching it, as shown. The two spheres are slightly separated, and the rod is then withdrawn. As a result, which of these? Well, if I bring negative charges there, that means that I'm going to have positive charges here and negative charges here. So L is going to be positive, and M is going to be negative. So that's number 6 is E. Actually, on this, when I change this, I'll edit this on the test. I'm going to make this a positively charged rod, just as it's drawn, and then that will make this negative and this positive. And then I will just change this word to be positively charged rod. So that's number 6. Number 7, two small charged objects attract each other with a force F when separated by a distance d. You reduce the charge on each object to 1/4 of its original value, and the distance between them is reduced to half the distance. So we start with Coulomb's law. And I am reducing the charge on both of these to 1/4 of its original value. So I get a quarter Q, and I'm reducing the distance by half, so I get a half there. So in the numerator, I get a factor of 1/16. In the denominator, I get a factor of 4th. If I simplify that, it's 4 over 16, which I will have 1/4 the force. So C is the right answer for number 7. Two particles, X and Y, are 4 meters apart. X has a charge of 2Q, and Y has a charge of Q. So I have 2Q and Q. The force of X on Y, this is the X force, this is the Y force. How does it compare? Is it 4 times the magnitude, twice the magnitude, the same, 1/4, or half the magnitude? It doesn't really matter about the distances or the difference in the charges. They're always going to have the same magnitude. Newton's third law are also from Newton's Coulomb's law. Two identical charges exert forces of 4 newtons on each other. They're 2 meters apart. What's the value of each charge? Simple application of Coulomb's law. Here I'm looking for Q, and Q is identical. So I can write this as KQ squared over R squared, just because Q is identical, and then I can solve for Q. That's going to be FR squared over K. Square root of that, 4 newtons. The distance between them was 2 meters. And I get 4 times 4, that's 16 over 9 times 10 to the 9th. And square root that. 4.21 times 10 to the 5th, negative 5th, rather. So C is the right answer for number 9. So this arrangement of charges, they're at the equilateral triangle. That means they're equidistant from one another. Which of these directions the net force on the plus 4Q? So let's consider this charge. The direction of the force is in this direction. And then let's consider this charge. The direction of the force is in this direction. And it's smaller because it's a smaller charge. Now, I know that neither A nor D is the answer. It's going to be somewhere in between. And because this force is bigger, the net force is going to be closer to that vector. So C is the right answer for number 10. So this arrangement of particles, what is the net force on the plus 3 microcoulomb charge? Or what is the direction, excuse me, of the net force on a plus 3 microcoulomb charge? All right, well, notice I have equal charges here and here, and so they're going to exert equal forces on there. Now, because of that, the net force is going to be at an angle of 45 degrees in that direction. All right, so that's 45 degrees below the positive x-axis. What is the electric field at a distance of 3 meters from a 1 nanocoulomb charge? Remember, electric field is just KQ over R squared. That's 9 times 10 to the 9th times 1 times 10 to the minus 9 over 3 meters. You have to square that. But those cancel. That cancels, so I'm just left with 1. A is number 12. Number 12 is A. Proton is 3 meters from a 1 nanocoulomb charge. What initial acceleration does it experience? Well, look, this is what I had up here. So I know that the electric field is 1 Newton per Coulomb, right? And I know that the force then is Q times E, which is going to be 1.6 times 10 to the minus 19 times 1, so it's just going to be that number. And then A is F over M from Newton's second law. Is going to be that force. Which is about 100 million meters per second. So B is the right answer for number 13. Two charged particles are arranged shown in which region of the electric field equal to 0. Well, let's just pick some points. So I'll pick this point. The electric field due to this negative charge will be in that direction, and the electric field due to this charge will be in that direction. So it can't be 2. Let's look at 3. All right. The electric field due to that negative charge is going to be towards the negative charge. And the electric field due to this charge is going to be away from that charge. Now that could potentially be 0, but notice that I'm closer here to the bigger charge, so the bigger charge is going to contribute a larger electric field. So I really want to get farther away from this big charge right here to have 0 electric field. So let's imagine here, the electric field due to the minus 4 Coulomb charge will be in that direction. Because I'm further away from it, the electric field is smaller than it was here. The electric field due to this charge will be in that direction. So only in region 1 can you have 0 electric field. Okay, let's see. Have a charge floating in an electric field. This is pretty much identical to a homework. I want to know what is the magnitude and direction of the electric field. First of all, it's a negative charge, so that means that my electric field has to be down so that my electric force is up and my weight is down. And then I can say that that electric force, which is equal to QE, is equal to mg. So the first part of the problem, I say that, well, it's downwards. Okay, so I can get rid of A and D. And then I just want to solve for the magnitude. I know it's either 1 or 10. So here I say 1 times 10 to the minus 9 coulombs. The mass of the electric field is also 1 times 10 to the minus 9. Oh, I'm sorry, the mass of the particle times g, which I said to take 10. And so that cancels with that, and just leaves me with E is equal to 10. So C is the right answer for number 15. Consider the charges in this figure. Which of these statements is true? Well, the field lines are coming out of the charges, so they both have to be positive. So that gets rid of this one and that one. And if you count the number of field lines, there are 11 field lines on both sides. That means that both charges are positive and both charges have the same magnitude. So that is A for number 16. A proton is accelerated by this constant electric field, moving in the same direction as the electric field initially at rest. What is the distance the proton moved after this amount of time? This is a homework problem. So first I want to find my force. The electric field is 300. Oh, what am I looking at? This gives me the force in newtons. 4.8 times 10 minus 17 newtons. And then I can find my acceleration, which is going to be F over m. So I'm going to divide that by the mass of the proton, which is 1.67 times 10 to the minus 27. And I get 29 times 10 to the ninth meters per second squared. And then I want to know the distance. Well, I know that x is equal to 1/2 at squared. That's assuming it's initially at rest, which it says it's initially at rest. So I take that acceleration and multiply it times the time squared times 1/2. I get 0.01 meters. So it moves a centimeter. Where the line is potential equal to 0. This is similar to one that we've had before. Here, let's see, I'm different distances from those, so no, it's not A. Here, I'm an equidistant from there to there, and there to there, and there to there. So all those positive and negative charges, their potentials are going to cancel out. So B is the right answer, and I'll leave you to go through the rest of them. Which of these is a conservative force? Okay, field forces are conservative. That would be 1 and 3. So C is number 19. Two charges are shown. What is the potential at point A at this point? So I found my potential, which is going to be the sum of KQ over R for both. All right, so that's going to be 9 times 10 to the ninth, that's K, times this charge, which is 9 times 10 to the minus 9, divided by R, which is 3 meters, plus 9 times 10 to the ninth, times negative 4 times 10 to the minus 9, divided by the distance, which is 2 meters. Now let's see, these cancel nicely. This 3 gives me a 3, so I get 27 minus 18, which is equal to, what's that, 9 volts. So A should be 20. Yeah. All right. A charged particle sits in an electric field as shown here. The particle follows a path shown by the dashed line. How much work is done to move the particle? It's moving along an equipotential line, so it has no change in potential or no change in energy. That means that there is 0 work. What is the potential in an electric field at the point P in, which is in the center of this square? All right. First of all, I have equal numbers of positive and negative particles, so V is equal to 0. And then also, if I draw my electric fields, I have the electric field due to this charge in that direction, due to this charge in that direction, due to this negative charge right there, and right there. So E is not equal to 0. E is in that direction, but V is 0. So that would be B for number 22. Consider this charge. The arrows represent field lines. The dashed lines represent equipotential lines. What is the sign of the charge? Well, field lines are coming out, so the charge is positive. And where is the electric potential least? Remember, V is KQ over R. The further I move away from a positive charge, As R goes up, V goes down. Okay, so here A is furthest away, but also D. A and D are on equal potential lines, and so they have the smallest, so E is the right answer. Unit of electric potential, the volt, is dimensionally equivalent to what? Remember, voltage or potential is energy for charge, so that's going to be a joule per coulomb. That's B for number 25. All right, 2 coulomb charge crosses 2 plates separated by this distance. The high potential plate is 5 volts. The low potential plate is minus 5 volts. How much kinetic energy does the charge have moving across these 2 plates? It's a similar question what we've had before, but I made it a little bit differently where I gave you the potential between the 2 plates, the potential on each plate, so that the potential difference here is going to be 5 minus negative 5, or 10 volts. So we have a potential difference between these two of 10 volts. Now the distance there is irrelevant. It doesn't matter about the distance. Okay, so if I want to know how much kinetic energy, that energy is going to equal to the work done by the electric field, which is going to equal Q delta V. And that Q is 2 coulombs times 10 volts, which is 20 joules. So A is number 26. Electron is released to position A in the potential described by this function. Where does it travel? What direction? Well, remember, I like to set up my plates. Here I have a high potential, low potential. Electric fields run in this direction. If I let a negative particle go here, it's going to move to the right, which is from low to high. So this particle going here is going to tend to move in this to the left, which would be to a higher potential. What amount of work is required to assemble this collection of charges? All right, so we have 3 things we need to calculate. Do this a little bit differently. Just sort of started doing this differently in class the other day, but or you can do it the way that we did it in some of the previous exams. But let's calculate the potential energy for these 2 charges. Remember, potential energy is KQQ over R. So that's going to be 9 times 10 to the 9th times 2 times 10 to the minus 9 times 1 times 10 to the minus 9 divided by R, which was 3. Those cancel. That cancels and leaves us a 3, so that's 6 times 10 to the minus 9. So our first one is 6 times 10 to the minus 9 joules. And then we need to do that twice more. So let's calculate the potential energy due to those 2 charges. It's going to be 9 times 10 to the 9th, 3 times 10 to the minus 9, and 1 times 10 to the minus 9, divided by the distance between them, which is 4. Let's see, so that cancels 27 over 4 times 10 to the minus 9. That's going to contribute. And then let's do these 2 charges, noticing that this distance is 5 meters. This is a special 3, 4, 5 triangle. And I'll calculate that over here. 9 times 10 to the 9th, 3 times 10 to the minus 9, 2 times 10 to the minus 9, divided by 5. So let's see, that cancels. I get 27 times 2. 54 over 5 times 10 to the minus 9. And then I add these 3 terms up. You might have it in decimal form, if that's fine, but I'm going to do it in fractional form. I get 24 times 10 to the minus 9, which is 2.4 times 10 to the minus 8 joules. So that's the amount of energy that is held within those charges. So that is C for number 28.